Welcome to HCTV's live interactive program that's part of St. Louis.
The whole production is pulled together.
It's going to be a steel bridge.
The way the cockpit is designed.
The highest rated green building in the world.
Welcome to HCTV Live. Welcome to the St. Louis University Earthquake Center for today's HCTV Live program, The Science Behind Earthquakes, the New Madrid 200th Anniversary. Hi everybody, I'm Tim Gore, your host for HCTV Live, and I'm very happy to welcome you here to the campus of St. Louis University and the Earthquake Center, where today we're going to be joined by Dr. Bob Herman from that wonderful Department of Earthquake Science. Thanks for being here, Bob.
Nice seeing you.
As always, we're going to be interactive throughout today's program. We're being joined by video conference schools from around the country. I'll be coming to those video conference schools for questions throughout the program. I'll ask all our video conference schools to please keep their microphones muted until I come to you guys for a question. Then unmute your microphone. Then, of course, remember to mute it again so we can come back here to Dr. Herman and get your answer. If you're joining us via television or the internet, then you can email us your questions throughout the program to live@hectv.org. That's live@hectv.org. Those questions are designed to come straight to my phone here. So if life is good, as we happened with the morning program, we'll hear lots of little dings going off on my phone, and we'll be able to incorporate your internet questions and your email questions as well. That's live@hectv.org. It is, if you didn't know already, the 200th anniversary, basically, of the huge New Madrid earthquakes, which occurred in December, January, and February of 1811 and 1812. The St. Louis University Earthquake Center wasn't around, obviously, at the time of the New Madrid quakes, but has all sorts of things to do with earthquakes today. Bob, why don't you share for the audience a little bit about you and what the Earthquake Center does?
Okay, I'm Bob Herman. I'm in charge of the St. Louis University Earthquake Center. We've been recording earthquakes for over 100 years. The first instrument went in 1909. And what we do is we put instruments out in the field, we make sure they work all the time, and then we send our data streams to the U.S. Geological Survey so that they can locate earthquakes. Not only the earthquakes here, but earthquakes in other parts of the United States and also worldwide.
And actually behind us, you're seeing a little bit of that activity happen because, Bob, I'll let you switch over to this side so we can talk a little bit about this. This actually represents seismic activity that's happening at different stations right now.
That's right. We have instruments in the ground, and whenever the ground moves, we'll have a recording of that. And right now we're looking at live ground motion, at least for the last 5 minutes, from what moved in St. Louis, Missouri, or down in Memphis, Tennessee, or in other sites in Missouri or Illinois. So that's the neat thing today about the internet and all the connections that we have, is that we can look at everything almost in real time.
Well, let's give the students a little bit of basic information just about the definition of an earthquake. When we talk earthquake, what are we saying?
Okay, what an earthquake is a rapid movement of two parts of the earth on a fault where the things move side by side. Now, this is caused by the heat within the earth, which provides the energy for the movement, and the particular process either could break new rock, break the rock to make the first fault, or in many places in the world, the fault is there and the earthquakes keep repeating on that particular fault.
Well, we want to give you an idea of where all these earthquakes happen around the globe before we talk a little bit more about what causes the earthquakes to happen. So we're going to go through a number of images here for you. First, we're going to start with an image of the map of the world, our global map, which shows you hot spots around the world which have earthquakes. You're going to see all of these red spots. In the Pacific area, of course, that's known as the Ring of Fire. All those red spots represent where lots of earthquakes happen, right, Bob?
That's right.
And if we go to our next slide, you'll actually see something called the plate tectonics. And let's talk about these plates and what are tectonics. The Earth has all these plates that are moving around?
That's right. Basically, about 40 years ago, people put together a lot of evidence and came up with this idea, and that the surface of the Earth is very cool in rock, and rigid and brittle, but the surface of the Earth is always moving. And we have these little sections called plates. Whenever they bump into each other or move with respect to each other, interesting things happen. Mountain building, volcanoes, and of course earthquakes.
And if we go to a map of the United States, this shows you where obviously most of the earthquakes are going to happen, or the most likely nature of earthquakes are going to happen in this country. We're located in St. Louis, right on the eastern side of Missouri, just south of the confluence of the Missouri and Mississippi rivers, and just south of us, you'll see that big red purplish place, which of course would be the New Madrid Fault. 200 years ago this month and next, big earthquakes happened. Over on the west coast along California and Washington, you see a great deal of earthquake possibility. And up with our friends friends in Alaska, we've got students joining us from Sandpoint, Alaska this afternoon. We see there's all sorts of earthquake activity too.
That's right. And these maps are used or produced by the U.S. Geological Survey, and they're actually used for preparing for earthquakes and for designing buildings to be safe during an earthquake.
Well, let's spend a little bit of time about what causes an earthquake, what that means. And students, as we begin to think about what causes earthquakes and how the earth actually moves, we'll be coming to you in just a few minutes for your first series of questions. So be thinking about what questions you want to ask about the natures of earthquakes, why they happen. So what do we need to know just to understand the basics, Bob?
Well, the basics, what is an earthquake again, and what does an earthquake do? And I said before, one type of earthquake would be the forces in the earth cause a rock to break. Now, we can take any piece of wood, a stick, or this shim, and we know that if I put a force on it, it's going to break. It's also going to make a sound and might make a loud sound. But the other thing that's important about this, I know it's going to break, but I don't know exactly when it's going to break. So if I go ahead and break it, we hear a sound. Well, when an earthquake occurs, a lot of the energy goes into the breaking and into this deformation here, but other energy goes into waves which will propagate. Those waves can cause damage at large distances.
So we've got waves going all over the place, and these earthquakes are happening in different ways depending upon how the different plates of the earth are shifting against each other.
That's right.
We've got some animations that we want to show you some examples of the different way the earth shift. The first is what's known as convergent, and in this instance, the plates are like moving in on each other.
They're going to bump into each other, and either one or two things are going to happen. One plate's going to be forced down underneath the other plate. As a result of this wet, cold material going down deep and heated, we're going to have volcanoes popping up. This is what's going to happen in Alaska along the Aleutian Island Arc, what happens in Japan. And the other possibility is when the two plates come together, they buckle up. And this is what would form the Alps, what has formed the Himalayas and the high mountains of Asia.
Okay, very good. So that's when the plates are coming together in a convergent nature. There's also the divergent when they're actually moving apart from each other.
Right, and that occurs typically out in the mid-ocean, middle of the oceans. It's called the mid-ocean ridge rift system. There's a pulling apart. The earth is weak there. You'll have volcanic activity. If you look at a map of the world, you're going to see a vast underwater mountain range that just encircles the earth. There are a few places in the earth right now where it's starting to split apart. And if you look at a map of where earthquakes occur in East Africa, you go from Ethiopia down to Kenya, what you're going to see, the Great African Rift System, there's a portion of Africa where it's pulling apart now, and that chunk of Africa in the future is going to make a huge, another continent, or certainly a very large island.
So there's convergent and there's divergent. Now let's look at what's called strike-slip faults.
Strike-slip fault, instead of the plates moving apart, they just move side by side with respect to each other. Places where that occurs would be out on the San Andreas Fault in California. There's a fault system in Turkey called the Anatolian Fault System, and there's a major fault system in China which has that particular motion. Now, this type of motion where things are moving side by side, you can have that in individual earthquakes that are not in a plate boundary. And many of the earthquakes in northeastern Arkansas are little strike-slip earthquakes.
So when we think about the New Madrid zone, is it strike-slip?
The New Madrid zone has a section of some sections of strike-slip where the two sides of the fault are moving with side by side, but there's also a little buckling occurring right down underneath the Mississippi River.
And you mentioned San Andreas in California. It's a strike-slip, and so
right.
When they talk about way, way, way forward in geologic time, is it the possibility that at some point California will split off?
Well, they can also talk way back in geological time that some of the rocks up near San Francisco really line up with the rocks down in Southern California. If you would run the movie back right now, if this is San Francisco, and this is California, so the rest of the United States is this way, it's moving that. So they can run the movie back and take these rocks and line them up. The future part of what's happening is the section west of the San Andreas is going to be moving toward Alaska.
Okay.
So
excellent. Okay.
Hollywood's going to be in Alaska in 10, 20 million years.
Well, that might change a great deal of what movies are made. We're going to go up to Waunakee, Wisconsin. Hello, Waunakee. Teacher, come in and say hi. Let us know what student might have a question right now about earthquakes.
Hi, hello Tim. I have Kenzie here who has a question for you. Hi, Tim. How do you know tectonic plates are there?
Oh, Kenzie, that's a great question. How do we know the tectonic plates are there? I mean, what caused them to figure out this theory?
Well, there is all sorts of evidence, one of which, where do the earthquakes occur? They line up generally in nice linear patterns. Where do volcanoes occur? They occur out in the middle of the oceans, the Atlantic Ocean. They also occur around the perimeter, the rim of the Pacific Ocean. We could also look at the earthquakes themselves, and if we study individual earthquakes, and there have been researchers at many places, St. Louis University, Father Stouter did that. He actually looked at individual earthquakes and saw, did it move this way, or they come together. By putting together all those pieces of evidence, they came up with this as a good model that fits everything.
Oh, very cool. Great question, Kenzie. I look forward to coming back to you guys in Wisconsin again later in the program. Let's go to our friends in Sandpoint, Alaska, who may be caring a great deal about earthquakes. You guys may get shakes way more often than we do down here in Missouri. Sandpoint, a question from you?
Hi, Tim. This is Mrs. Lee with our 4th grade class. Logan has a question.
Hi. Can you tell me where the next earthquake is?
Oh, a cool question. Is it Logan, I think it was? I hope I heard that right. The question is about predictability of earthquakes. Can you tell when the next earthquake is going to happen? How would we know that the earthquake might be about to happen?
We can tell on the short period of term, let's say in the days and weeks or so. We can have an idea in the 10, 20-year period, and certainly in a long period. One idea, if we look at where big earthquakes have occurred, and let's say around the Pacific Ocean, which would include Alaska, the west coast of the United States, west coast of South America. We have the idea of plate tectonics that says, hey, big things are going to happen. And when an earthquake occurs, a big earthquake occurs over a certain range of distances. And what people have noticed is, looking at the history of the earthquakes in the last 100 years, there have been little sections where nothing's happened. It's called a gap. And that would be a place where we would expect earthquakes to occur. So on the longer time, we can look at, let's say, probabilities. Let's say in the San Andreas Fault in California, every 200 to 300 years, you would expect to have a big earthquake. And so we can use that information to plan for the future.
Oh, excellent. You talk about hazards and the likelihood of them. And students, we've got some maps we're going to show you, which gives you the idea of earthquake hazards and possibilities in your particular area. We're going to go first to what's going to be the examples from Wisconsin. This will be images 8 and 9 to the technical staff there back in the director's booth. We're going to go to Wisconsin so you guys can see the likelihood of earthquakes here. And you guys are going to notice that there isn't much possibility here, right, Bob?
That's right. The hazard in Wisconsin comes from earthquakes in northern Illinois. There have been some earthquakes. Just a few years ago, there was just one west of Chicago that was felt up near LaSalle, Peru, Illinois. Wisconsin basically is not deforming right now and really is not expected to have any real earthquake problem at all.
And there we have a map of Wisconsin where you can see the geography. The green obviously represents the terrain. If there were earthquakes happening in Wisconsin between 1990 and 2006, you'd see orange dots all over the place. And you'll notice, Bob, in Wisconsin, I just am not seeing orange dots.
That's right.
However, to our friends in Sandpoint, Alaska, when we go to you, our friends in Wisconsin will probably figure out that there's going to be a great deal of difference. So let's go to the images which show us the Alaska likelihood of hazards. And Bob,
that's the hazard map that's going to give you the expectation of having very strong shaking sometime in the future. We see the Aleutian Island arc where the Pacific plate is bumping into the North American plate. And that plate extension goes inland up to about Fairbanks. Anchorage is the major city in Alaska, and that certainly is affected by earthquakes. And then we have the west coast of Alaska is also affected by earthquakes.
So you can see that a lot of earthquakes are likely to happen in Alaska, and we certainly see that here between 1990.
This particular map is interesting that the colors indicate how deep the earthquakes are. Red means shallow, green would be intermediate, and then the blue are several hundred kilometers deep. If we were to take a slice there and make a plot, what we would see is a mapping of the plate being forced down underneath the Aleutian Island arc.
Oh, very cool. We've got an email question that's actually come in for our students up in Alaska. So I want to go to our students in Sandpoint to answer this question, which is coming from an internet viewer. Students in Alaska, how often do you guys feel quakes up there? Let everybody know where Sandpoint, Alaska is, and how often do you guys feel quakes?
We are about halfway down the Aleutian chain. We're actually on an island, and so we feel earthquakes probably two times a week, do you think? Sometimes the earthquakes are rather mild, but last year we actually had one earthquake where we actually had to get under our desks.
Oh. Well, hopefully during our program today, we won't have to have you get under your desks again. They felt one where they actually had to get under the desk, but most of the time they're pretty mild. And that's going to be true for all areas where there's seismic
do they have
activities.
practice up there? What
Do you
to
guys
do
have
on an earthquake?
Do you guys have earthquake drills like other places have, like tornado drills here in the Midwest?
We don't really practice, but we do all know what to do just because we live with earthquakes every day.
Very good. Thanks very much for that information, Alaska. I really appreciate learning that from you guys. So we've talked a little bit about the nature of earthquakes. We've gotten some questions about the nature of earthquakes and the seismic activity there. We're also being joined by a school via view-only video conference from Alabama, and I wanted Alabama to have a chance to see the likelihood of earthquakes in their area as well. So we'll bring up our Alabama hazard maps now so you guys can see the likelihood that you guys might face such a dilemma at any point in time. So we'll bring those up. And here you go. Right now, I'm seeing some light blue, so we're saying not too often, but something evidently is coming from the north. Is that from the New Madrid?
Well, basically, up in the northwest, they're going to be affected by earthquakes in the New Madrid size. You know, a big earthquake can cause shaking at large distance, and that's what we're seeing there. We also have some earthquakes up in the eastern Tennessee seismic zone. There was an earthquake in the last 10 years at Fort Payne, Alabama, just by the Georgia border, that was widely felt in the area.
Oh, very good. We've got another internet question that's come to us about what's best. The Alaska kids mentioned getting under desks. Is it still a good idea to get under? Is that the best option, under heavy pieces of furniture in doorways, they ask?
Well, the important thing is you don't want to be injured. And if you aren't, so one way of the buildings is falling down, you want to not be hit by anything. Down here in the Midwest, we worry about tornadoes, which will blow glass and cause building damage. So big desks, heavy desks are a good place to be. Certainly, if you're away from anything that can fall on you, such as you're outside and away from trees and utility poles and automobiles, that's a safe place to be.
Let's see if students have any more questions about the nature of earthquakes. And then, folks, we're going to begin to look at some of these pieces of equipment here as we begin to talk about how earthquakes are measured and all that kind of good stuff. So let's go back to Wisconsin. Do you all have another question right now for Dr. Herman?
Would you know where the most deadliest earthquake has struck?
Oh, that's a cool question. Do we have any sense of like where the deadliest earthquake has struck? Or?
Well, we do have earthquake history. China has an earthquake history going back 2,000 years. In the Middle East, around the Mediterranean, there's a history which goes back almost about 3,000 years. We know there were big earthquakes in China about 300 years ago that killed something in the order of 1 million people. There was an earthquake in 1976 in northeastern China that killed about 250,000 people. We also know that in 2004 we had a big earthquake off of Indonesia that caused a tsunami, the big sea wave, which killed hundreds of thousands of people. So yes, China has been always affected by earthquakes. The whole range starting from along the Alps going into Turkey, Iran, Iraq, Pakistan have always had earthquakes that have caused many deaths.
Thanks for that question, Wisconsin. We'll come to you guys again. Let's go back to Alaska. Another question from Sandpoint. Our friends in the Aleutians.
Hi, Tim. We have a question from Lila.
If the earthquake is deeper in the earth, does it cause more damage?
Oh, if an earthquake is deep, cool question. If an earthquake is deeper in the earth, is it more likely to cause more damage?
There are two things that affect, well, what affects ground motion, or the damage is how great is the shaking.
How great is the shaking?
And there are
causes
two
the
things
damage.
that affect shaking, distance and size.
Okay.
So for a given distance, the bigger earthquake will cause a greater shaking. For a given size of the earthquake, the shorter distance will have much greater shaking than an earthquake at larger distance. So it's the combination of the size of the earthquake and the distance that'll make an effect. So yeah, certainly we know that there are big earthquakes under western Brazil, believe it or not, but those earthquakes are down 500 kilometers, and that's so far away from where people live, it's not going to do anything.
Oh.
So sometimes a very shallow earthquake, somewhat small, can cause major destruction, and then a big earthquake that's as deep will not cause anything.
Well, that question from Alaska and your answer, Bob, provides us a really nice segue to go to some video we want you guys to see of earthquakes themselves, the damage after or things happening during an earthquake itself. We've pulled together some archival footage for you. The first part of it's going to show you the damage after the 1906 earthquake in San Francisco, perhaps one of the most famous, and that's what we're looking at here. And so, Bob, in 1906, this image we're seeing now is actually after the earthquake. It was a big earthquake, but we had a serious problem with the fire also.
Yeah, this is one of the largest earthquakes in the western United States that we know about. It was a very long section of the San Andreas Fault that moved. Much of the area was just farmland, but the city of San Francisco was there, was damaged because of the earthquake, was destroyed because of the fires. And the reason there were fires is that the earthquake damaged or broke the water mains that would be used to put out fires.
And here we're into Alaska.
Alaska,
1964.
There was a tsunami generated that killed some people up in California. The other things that happened and we learned there is that there's a certain type of soil that's not very strong, and because of that shaking, it becomes very much like a quicksand and buildings sink. So we learned about liquefaction. There is a classic picture of an earthquake, the Niigata earthquake in Japan, 1964, where the tall buildings just tilted over, like they didn't fall down, but they tilted over on their sides because the soil underneath became weak and could not support the building. And now we have the big earthquake in the Tohoku earthquake in Japan that had just occurred earlier this year. Now what we have is we got video cameras, we have cell phones and everything else, and what you're seeing here is just what will happen in a grocery store if the building is shaken.
So those earthquakes, of course, were pretty darn big. The San Francisco earthquake,
At least an 8.
the 64 one,
In Alaska, a high 8, if not a 9.
and the one in Japan was a 9, or pretty?
Very close to a 9. So the Tohoku, the Japan earthquake, the Great Alaskan earthquake are some of the largest earthquakes in the last 100 years.
And as we talk about the 8s and 9s, this is probably a good chance to mention how we measure earthquakes. The magnitude, that's off the Richter scale.
Right. What we do when we measure earthquakes, we have to have a recording. It's called a seismogram. And then what we look at is just how big is the movement of the signal on the seismogram. And we put that into a simple calculator, and we come up with a number. So what we have here are some of the instruments. As I said earlier, we've been studying earthquakes here at St. Louis University since 1909. And we just have some of the older instruments and also the newer instruments on display.
Well, you just mentioned seismograms, so let's begin to look at some of them.
Okay.
This is an example of a seismogram.
Right, and the word, all words have a meaning. Seismogram, two Greek words, seismo meaning earthquake, gram meaning to write. And this is a recording. There's a little drum. We'll see the drum in a second that rotates, and it writes a little spiral on a piece of paper. So here time is going to increase. This is 1 day's recording. Time's going to increase from left to right, top to down. We're going to have little marks on here that indicate minutes, different marks that are going to indicate hours, because we need to know when did the signal come here. What was the day, year, month, day, hour, minute, and second that the signal came in. This particular recording here are 2 earthquakes that occurred in northeastern Arkansas in 1976. Near the town of Marquette, we got a magnitude 5 earthquake and a magnitude 4.5 aftershock. We see that everything is relatively, a few wiggles beforehand, but you can really see that something happened here. And in this one here, we actually see the P wave coming in and the S wave.
Now, you've mentioned P wave and S wave
Right.
before. What's a P, what's an S?
Okay, there are 2, in an elastic medium, there are 2 waves that are propagate. One is going to be like a sound wave in which the wave propagates out and the ground moves in a direction of propagation, a push-pull wave. And the other one, which actually is bigger in amplitude and it causes the damage, is that the wave goes out, the ground moves in a perpendicular direction. Those are called shear waves or S waves.
Okay.
The P wave is faster, the S wave is slower. The time difference between the P wave and the S wave will tell us actually how far away the earthquake was from the seismograph station. So we could look at this thing here and say how many kilometers it was from St. Louis down to Marquette, Arkansas.
Now, this seismogram looks a great deal like what I'm seeing when I
Right
look
here.
at this drum.
This is an old recorder. It's a self-contained seismograph system. It's got a clock because we want to know time to within 1/10 of a second a day. It's got a recording drum, so the drum is turning right now, and the pen is moving horizontally across. So in a way, it's writing a continuous spiral that when we take it apart, we get a long piece of paper. We've got time marks on there. The other thing we've got that makes this a seismograph, this is the recorder. We have the sensor. And what the sensor is, it's going to convert the shaking of the ground into an electrical voltage, which then the recorder sees. Now this is very sensitive. Tim's just going to go up and down. Well, that's one way to move the ground.
So the earth is moving under my feet in a metaphoric sense.
Right. Well, you can put it on the table, and he's going to go up and down just to show you how sensitive it is. Well, you don't even have to jump. You can
I like jumping, Bob.
You can go up and down on your toes like this. No jumping, and it's sensitive. So this is an instrument that measures the movement of the ground. Anything that causes the ground to move, we will see. So that means if there's a windstorm going by, if there's a truck going by, if students are walking, trains, if there are waves generated because of storms out in the ocean, we'll see that. And I've got some recordings here. Or if there's an earthquake, we're going to see that particular signal.
Well, now we've got some other seismograms as well we want to look at.
Yeah, the other seismograms we got here, just you notice that this one is not as quiet as the other one. Yeah, here's a little earthquake there. This particular thing is noisy, and the reason it's noisy is there were storms out in the Atlantic Ocean that the sea waves then interacted with the ground, and that propagated over large distances, and we see that. So what we can do with seismographs depends upon the time of the year. Early summer is very quiet. We can see a lot of things, and then in the winter we're going to see the effects of storms, and it's harder to do what we have to do. This one here is another recording, a different scale, where we got a local earthquake, maybe a distant earthquake. By looking at enough of these, we can tell which is a distant earthquake.
Now this is very cool. This is very old.
Very old. What we have here is an original recording. The previous ones were pen and ink. This is a recording on smoke paper, and it's from an earthquake in 1911, recorded in St. Louis. And we're going to see what the instrument was that recorded that in a few minutes. We can come down here. What we would do is you take a piece of paper, you hold it over an alcohol lamp that would put some soot on it. It's put on a recording drum, and instead of putting ink on the paper, the drum had a little needle on it, and it scratches off the smoke.
Oh.
And then at the end of the day, if there's nothing on there, we recycle the paper by resmoking it. If there is something on there, they would just dip this in shellac, and that's why it doesn't come off in my fingers after 100 years anymore. What this said for this earthquake is the recording was about this high, and that meant that the ground moved up and down about 1 millimeter in St. Louis. So this was a big earthquake in 1911.
And the machine here that would have recorded that earthquake is actually in the corner of this room. We've got some videos so the students can see this.
Right. That machine was purchased in 1909. A number of universities in the United States purchased the same instrument, and they were here as sort of basic research. Let's learn something about earthquakes. Let's learn something quantitative about earthquakes. So this is a negative of the original recording from the earthquake in 1910.
Oh, very cool.
Now what we have, since we've got an archive of all these recordings, we have other interesting earthquakes that might be of interest. Here's one where everything is sort of quiet, continues on, and then all of a sudden,
massive activity.
The pen, in this case, the light beam, this is photographic paper, went all over the place. This is the recording of the March 27th, 1964 Great Alaskan Earthquake, which really affected the Anchorage area.
So this is the seismogram of what we just saw on video.
And what we know by looking at this was a big earthquake. But we also note that the lines overlap, and it's very difficult to use this particular piece of paper to study the earthquake. And we have other recordings of that same earthquake.
Very cool. Let's see what other questions students have. We're going to be looking at some other pieces of equipment in a bit, but let's see what questions you guys still have for Dr. Herman. Let's go back up to Wisconsin first. Wisconsin, a question from you.
Hi, yes, Tim. I have Maddie here. We've been learning a lot about oceans and ocean movement and the tectonic plate, so she has a question about earthquakes and how it relates to the ocean.
How does the movement of tectonic plate change the geography of the ocean floor?
Oh, that's a very cool question. You have been studying about the oceans and tectonic plates. How does the movement of tectonic plates affect the ocean floor?
Well, the ocean floor is on a tectonic plate. It's moving around too. It's not really the motion, well, tectonic plate, it's really what happens at the place where the plates meet together. Right out in the middle of the ocean, you have the Mid-Atlantic Ridge, for example, which runs from basically almost the North Pole down into the Antarctic. And that's where the plates are pulling apart. But in the process, there are some huge underground mountain changes. You've got volcanism. You've got the island of Iceland is sitting right on top of the Mid-Atlantic Ridge. Volcanoes all the time. Big lava flows. So if you read the news, they're worried about eruptions. They're worried about, the heating of the ice underneath the glaciers and floods and everything else. So most of the ocean floor, once you get away from the mid-ocean ridge, it's just quiet. It's just old. It's been there a long while. It's cold. The only other place where it gets really exciting is at the other end, away from the mid-ocean ridge, where that particular plate boundary is bumping into another. That plate is bumping into another plate. The Pacific plate is bumping into the North American plate right along the Aleutian Island arc. That thing is Pacific plate is being forced down underneath the Aleutian Island arc. That material has been recycled into the interior of the Earth again. Some of the material carried down gets heated up, comes up, forms volcanoes, and that's why the Aleutian Islands are there. It's because of the volcanism due to plate tectonics.
And you can see that again as you guys look at that map of plate tectonics, which we've put up again for you. Let's go back to the Aleutian Islands. Sandpoint, Alaska, another question from you.
Yes, we have a question from Logan and then kind of a two-part from Edmund. So go ahead, Logan, and then Edmund.
Does the information go straight to the university or does it go to USGS?
Excellent. I'll get to that question in a minute, Logan. I'll go ahead and have Edmund ask his question now, too.
Do you put the sensors in the ground?
So the questions deal with the information and how it gets back. Does the information that's coming from the sensors go straight to the university, or are you getting it from the USGS or some agency coming to you? How does that work?
Well,
good questions, guys.
Today, a lot of the seismographs are connected electronically to computers that pick up everything. So we have instruments here in St. Louis. All our instruments are connected to the internet. We're shooting the data streams to the U.S. Geological Survey in Golden, Colorado. We're also sending them to our data archives. So anybody in the world who's interested in how the ground moved here can look at the seismograms. And whenever there is an earthquake greater than magnitude 4 in Alaska on land, I'll go get the recordings and analyze the earthquake. So it's really easy to do science today because of the internet access.
And Edmund's question had to do with, are you guys putting sensors in the ground? Do you have sensors yourself that you guys are doing?
Yeah, we have about 35 locations in 7 states. We've got Kentucky, Indiana, Ohio, Illinois, Missouri, Arkansas, Alabama, and Tennessee, in which we have instruments. And we put them in the area where we've had earthquakes in the past, because we want to know several things. When the next earthquake occurs, we want to have that thing located quickly so that we can estimate what the damage might be so that people can respond properly.
We've gotten some more email questions. I want to take this opportunity to mention that if you've got questions, don't forget to send them to us at live@hectv.org. And if you're one of our interactive schools in Alaska or Wisconsin, if you have more questions than you can think of right now, don't hesitate to email them to us. We'll get them to Bob and send you the answers later in case we can't get to them all during the show. This question deals with the magnitude of quakes changing after the initial reports. Like you'll hear a quake's like 6.5 and then it'll be changed like a 5.2 or whatever.
Well, there are different magnitude scales, and even the idea of magnitude confuses people. And the reason there are different magnitude scales is different parts of the seismogram sample different parts of the earthquake. So the first signal we see is the P wave coming out, and that's the fastest wave coming out. That sees the beginning of the earthquake. And then there are other signals that will come in that we have to wait 30 minutes or an hour to see those particular signals. Those signals are sampling the whole entire earthquake. So there are people that are going to use the magnitude or the signals themselves to say, okay, we had a big earthquake, but yeah, most of the energy was on this release on this part of the fault, and then it started moving in that particular direction. That's all very important for estimating what the effects of the earthquake might be.
Well, as you talk about that, this might be a good time before we finish with the equipment to show that video dealing with the transportable array so the kids can actually see this go out. So we'll bring that video up, and what you're going to see is where the earthquake starts and then move out. We may run it for you a couple of times.
Yeah, there's a major experiment right now in which 400 instruments are moving across the lower 48 states. As soon as the instruments hit the Atlantic Ocean, 100 of them are going to go to Alaska. And what we're seeing here is a little movie of how did the ground move from the earthquake in Oklahoma. And we could see the waves propagate out. And remember, it's at large distance, it's the shaking, the waves, the motion of the ground that is going to cause particular damage. This type of display was first developed by former colleague Chuck Langston at Penn State University.
I'm getting lots of, I love the beeps coming in. We're getting lots of questions, so let me see what this one is all. Oh, does an explosion from somewhere give a different kind of reading than an earthquake would be?
Yes, we also look at explosions, especially underground nuclear explosions, and there's a difference. And basically, the explosion pops off very quickly compared to an earthquake. An explosion occurs in a very small region of the earth, whereas a big earthquake over a large, the fault dimensions are very big. So that means that they're going to be the different magnitudes will give different numbers. And we can use that to say that this particular signal was due to an earthquake or this signal was due to an explosion. But that is still a major research area.
And a question that just came to us from our folks who are joining us via View Only in Alabama goes right with that. You can also tell if like it's a train going by or a large truck going by?
Oh yeah, anything that moves the ground, we'll pick it up. And if they go to our website and go to the station at Portageville, Missouri, they'll see all the coal trains going down between St. Louis and Memphis.
Oh, very cool. Let's look at this piece of equipment, because this is the inside of a
yeah, this is an older seismograph. This thing was built at least 60 years ago here in St. Louis, and it illustrates what a seismograph is. What we need is an instrument that gives us a recording of ground motion. And one part of it is a pendulum. So we see the thing moving up and down, that's a pendulum. Another part is we have to convert that motion into something we can use, like electrical voltage. In this case, we've got a coil wire moving in a magnetic field. That is an electric generator. That's going to generate a voltage. So what will happen if the ground moves, and I'm going to move the ground up and down, we're going to see that between here and here, there's going to be a difference. And so this particular instrument then will give us a recording that's going to be a representation of the actual shaking of the ground. That is technology from 60 years ago. The recorder we saw before was technology from 40 years ago. Things are getting better now. We are no longer recording on photographic paper or pen and ink. You know, everything's run by a computer today. We're running on, we record on, computers.
And that's what
And basically, the real reason for that, from the big Alaskan '64 earthquake, we knew there was a big earthquake, but we couldn't do anything with it because all the lines overlapped. Well, the modern instruments are designed to record a big earthquake on scale.
And these are some of those?
This is one instrument which is made in England that has sensors. So each one of these things, which measure a different component of ground motion, is like the big thing here. A lot of electronics in there for this thing to work. So this is designed to record small earthquakes nearby and also big earthquakes at large distance. This instrument here is about the same as that as far as what it will do. This was made in Canada. Inside here there are 3 sensors. This little instrument here has some of the capabilities of that one. It's certainly a lot more portable than this one. This is heavy. And then we have another instrument which is not very easy to break, because this thing is designed to record big earthquakes on scales. It's actually, you put this in a building as the building falls down. You notice in the bottom here, there is a clamp there so that this thing is bolted to the ground, so when you have a big earthquake, the instrument doesn't fly across. This instrument here, the recording of this thing is going to be of interest to engineers, because engineers want to know about destructive ground motion, and they really need to know what was the motion of the ground, what was the motion of the building, so they can figure out what happened.
Wonderful. We're going to talk about the New Madrid quakes here in just a minute, but let's see if you've got any other questions about the equipment or what we've talked about so far. So Wisconsin, a question from you.
Hi, yes, I have Drew here. He has a question for you.
Do earthquakes make islands?
Oh, Drew, cool question. Can earthquakes create islands? Or is that something that would be more true of volcanic activity?
Volcanoes create islands. Certainly an earthquake can split land apart. Right now in East Africa, between, you start at Ethiopia, going down to Kenya, to Uganda and Tanganyika. There's the Mid-African Rift Valley. It's got volcanoes in it. It's got a big depression. Plate tectonics is pulling that apart. Every time there's a jerk, that's an earthquake. That whole section of Africa will come apart someday and form another continent. So it's a big island.
Oh, very cool. Thanks for that question. Let's go back to Alaska. Another question from our phones in Sandpoint.
Yes, Edmund has a question he'd like to ask.
Has an earthquake ever broken one of the seismographs?
Has an earthquake ever broken one of the seismographs? Oh, Edmund, that's a cool question.
Not one of ours, but yes, if an earthquake causes a building to collapse, we'll lose the seismograph. We've had on some of the recorders that record on pen and ink, if the motion's too fast, it'll break the pen. Yes, if an earthquake can destroy buildings, an earthquake can destroy seismographs.
An email question from again in Alabama. Are oceanic animals affected by earthquakes and tsunamis? Do they know what's happening?
They don't know what's happening. Certainly anything that's living can be affected by earthquakes. We know that there are underwater landslides that would certainly affect life forms. If the earthquake causes the seafloor to raise up, if you're in a coral atoll, you could expose the corals to the air, they'll die. Yes, it can affect life on land. Certainly you have landslides and other things that will affect
cool.
anything that's living.
Keep those questions coming. We're going to talk a little bit about the New Madrid quakes, because obviously we picked this time of year to do the program because 200 years ago, this month, next month, and in February, the big New Madrid quakes occurred. How big were they? I mean, let's talk a little bit about them.
We don't really know how big they were in the modern sense, because we didn't have seismographs back then. We did have reports of that people kept in their diaries, or reports that were written down in newspapers. So by looking at the effects of the earthquakes and looking at the effects of modern earthquakes, for which we know the magnitude, we can estimate the size of the earthquakes. So one professor at St. Louis University, Otto Nutley, did some of the earlier studies in our area, and he estimated that by 1 magnitude scale, it was basically a low magnitude 7. Other people have estimated that it could have been a mid-magnitude 7 or even a high magnitude 7. And you notice I'm being very precise about low and mid and high. That's just because we did not have instrumental recordings.
Well, let's go to a couple of maps which will show you where they think those earthquakes occurred, and then show you the damage that they think is occurred from them. So this is an old map of Arkansas, Tennessee, southeast Missouri. They're the New Madrid, and obviously those bigger circles that you see in the darker red are examples of the major earthquakes. Smaller circles representing aftershocks or smaller things. And aftershocks, I mean, are happening with great frequency all the time right after an earthquake?
Yeah, after a big earthquake, because there's a disruption, a breaking, and you form a bunch of little cracks, and the things have to eventually adjust and weaken down. We also know that if you have a big earthquake, it might just set up the conditions for another earthquake to occur at the end. So if you got a big earthquake today, we really are starting to focus on what's going to happen, what could happen at the ends of the fault. So we had 3 big earthquakes, 1811, 1812. Otto Nutley thought they started way south of New Madrid, and then they moved closer, and the last one was right at New Madrid. And that would fit the idea that one of these was setting up the conditions for the next one to occur.
That's cool to hear. This next map will show you the idea of how far people could feel the damage from the quake. You may have heard the story about church bells ringing in Boston, for example, from the New Madrid quakes. Talk a little bit about what we're seeing here, Bob.
Well, basically, we can look at the effects of an earthquake. That's called an intensity scale. In the United States, we use a modified Mercalli intensity scale. The colors indicate the the degree of shaking. Red would be a lot of shaking, and as we go to the green, just a little bit of shaking where people would feel it. The original reports, as I said, would come from diaries or written accounts or newspapers, but at that time period, this was not really settled. The most western town was St. Louis, or a few communities here, which were established by the French in 1750s. Going west, the next community which would have had written history would have been in New Mexico, where you had towns were forming in Santa Fe and Albuquerque, and certainly way out west in California.
Now, St. Louis existed, obviously. The city of St. Louis existed at that point in time. And an email question came in. Did those quakes result in any structural damage in St. Louis that was recorded?
I think there were brick buildings in St. Charles, Missouri, which is about 30 kilometers away from downtown St. Louis, and there was some damage there. But most of the construction here would have been log cabins, and it's called the New Madrid earthquake because that little town, which was on the shores, was right on the Mississippi River. Because of the liquefaction, because of the severe shaking, that town disappeared.
Wow.
So there was strong shaking there. This was one of the first cases of federal disaster relief in the United States.
We've got an image of what are called sand blows for you because we want to show you that how do we know that the New Madrid Fault exists, what kind of activity is happening. This is an aerial photo of that area. What are we looking at here, Bob?
Well, first of all, this area is, people in northeastern Arkansas know, is a great agricultural area, and the reason for that is that the Ohio River and the Mississippi River have been depositing soils here for a long time. And as those river deposits go down, sometimes it's gravel, sometimes clay, and sometimes sand, and you have layers of sand under clay. When you have a big shaking, the sand particles will settle down. Any water in them will be forced up to the surface. Much like if you're walking in the beach in the summer, you walk down, you can wiggle your foot, and your foot will go in the water. That's the liquefaction. Here what happened is that the forces were so great with that water was pushed out. It took a lot of sand with it and brought that sand up to the surface. So people have done there, they've dug little trenches through here, and they were able to date earthquakes before 1811, 1812, because what they could see is they could see older sand blows, and then the newer, more recent earthquakes would have paths cutting through the older ones.
Oh, wow.
So that's why we know that there were big earthquakes. We know about 1811, 1812 because there are people like Audubon who did all the bird photo paintings, went through the area at the time. But 300 years before that and 600 years before that, there were also big earthquakes.
Wow. Students, let's see what other questions you guys have. Wisconsin, another question for Dr. Herman.
Yes, I have Jake here.
What time of year are earthquakes more likely to happen?
Well, that's an interesting question. Is there any relationship between time of year and earthquake at all?
Not really. People have been trying to do that, or time of day, because we know that the position of the moon and the sun change in the position of the sky. They affect tides in the ocean. They also cause solid earth tides, but there's no real relationship between any of those and whether an earthquake occurs or does not occur.
Okay, thanks very much, Wisconsin. Alaska, another question from you up in our northwest.
Yes, Edmund has a question, and then Devin.
How far can an aftershock travel?
Thanks, Edmund. I'll get to that question after we hear from Devin, I think it was. Devin, you want to ask yours?
Is it possible that there can be a big earthquake to move the whole Earth?
Oh, cool. That's a great question. Edmund's question is, how far can an aftershock travel?
Well, an aftershock's right near the earthquake, but an aftershock is an earthquake, so it's going to generate seismic waves, and those things can be felt to large distances. Here in the Midwest of the United States, because the rocks are very, very old, the waves will propagate very, very large distances. In California, they don't propagate as far. There are some differences in the efficiency of how these signals are how they are transmitted.
And Devin, your question is really cool. He wants to know, can a big earthquake actually move the Earth? And that leads me to think about what happened as a result of the Japanese earthquake recently.
Yeah, well, basically, yes. Big earthquakes can change the rotation of the Earth. Now, we all know what a clock is. We all know what time is, but I'm not sure if you realize that the people that worry about time, we might have leap seconds every year. And that's because the rotation of the Earth is not perfect, and it doesn't line up with the position of the Earth around the sun. So every once in a while, scientists will reset their clocks by a second or two. what an earthquake does, a big earthquake like the Tohoku earthquake or the big Great Alaskan earthquake will cause big vertical movements on the surface of the earth. The vertical movements, if it's on the ocean, will give rise to the tsunamis. Well, just think of the movies you've seen, or someone on ice skates, or a ballet dancer where they're doing spinning around, and we know when they bring their arms closer to the body, they spin faster. So if you were spinning around and you did this with your arms, you would go faster and slower. So the Earth is spinning around on its axis in space, and if anything moves the outside of the surface of the Earth up or down a bit, that's going to speed up or slow down the rotation of the Earth.
Very cool question. Don't forget, if you've got more, send them via email to live@hectv.org. Let's talk about the future of earthquake science as people begin to record and what they can do. Talk a little bit about something we know as the pager system, P-A-G-E-R.
That's right.
And what's it got? What can it do for us?
What the USGS realizes that out there at National Earthquake Information Centers, you can quickly locate earthquakes, but we also know that it's in order to save lives and to help people reconstruct after earthquakes, we really need a rapid assessment of what the earthquake could have done.
Well, let's look at this image and talk about what this is showing us.
Looking there is their map from their prompt assessment of global earthquake risk, which is developed by David Wald at the U.S. Geological Survey in Golden, Colorado. So after a big earthquake, first thing you do is where was the earthquake, and then how deep was the earthquake, and how big was the earthquake. Then you look at a database of where people live, and you can make an estimate of what those people should have felt.
Let's go back to that image as we talk about then as this particular example.
For example,
this
in
was
that particular
Oklahoma.
map, you have a map on the upper left which will have little contours in there, which would be the level of the shaking. On the upper right is a little summary that with colors indicating the communities and the number of people that would be affected by different degrees of shaking. A red would be very bad, could be damage. An orange could be minor damage. A yellow, people would shake and things would rattle around the house. Maybe green would be felt, and we'll get an idea of how many people would have felt the earthquake. And then to provide information, quick information of just how bad this could be, there's an estimate of how many people could be killed, and that's the color scheme on the left. And then there's an estimate of what kind of damage there would be. And this is very important that right after an earthquake, there's a lot, we aren't aware what the problem is, that the state and local governments can then focus on the area. They have an idea of what could have happened, and they know where it is, and then they could start getting the rescue crews.
So this gets out to them right away.
Right, within 10 to 20 minutes after an earthquake, and that's what they need.
Excellent. Let's go to final questions from our student groups. We've got about 5 minutes left. Wisconsin, a final question from you?
Yes, I have Toria here.
What's the average amount of earthquakes each year in the United States?
Oh, thanks, Toria. Do you have an idea about the average amount of earthquakes we get in the U.S. every year?
I know my area that we would have about a magnitude 5 earthquake right here affecting the St. Louis, Memphis area about once every 10 years.
Okay.
So that means every year we should have about a 4, and about 10 times a year should be something large enough to be felt. Globally, magnitude 9 earthquakes maybe every 10 to 20 years, and then we could count down from there. Certainly some places will never see a magnitude 5 right in their state, such as Wisconsin, whereas in Alaska, magnitude 5 is, it's almost common.
Alaska, you may not think of them as common when you're getting under the desk, but do you have a final question you'd like to ask?
Yes, hi Tim. Logan would like to ask one question about the fault zone in New Madrid.
Cool.
Okay, how is it created if there's no plates?
Oh, very cool. So he's asking specifically about the New Madrid Fault. How was it created? What's caused that to happen?
Those are good questions, and we don't really have answers for that. We know from the geological history that 500 million years ago, what is now the United States was pulling apart in a rift. It was a divergent plate boundary, but it stopped.
Oh.
And then about 250 million years ago, it started to pull apart again. So all we can really say is that this is a place that's very weak geologically, and that might be the reason why we have the earthquakes there. So our particular problem is, it's easy for Alaska. We've got the plate boundaries. We have the plates coming together. We're going to have big earthquakes, a lot of interesting things. Here we are in the middle of the plate, and there have been big earthquakes in the past. We don't know how this thing is recharging, so we can have big earthquakes in the future. and we don't really understand why. So it's a hard problem.
That's a great question. And don't forget, if you guys have more questions, send them to us at live@hectv.org. We'll send them to Bob. He'll give us answers and we'll send them back to you. Bob, we've just got about 3 minutes left. A lot of students may be interested in earthquakes a great deal. If they want to take their study of earthquakes or geosciences further, there's also career opportunities and things that they should be thinking about?
Oh, that's right. I mean, there are a lot of things that the science is used for, one of which is we study the interior of the Earth. Well, if you're not interested in the deep interior of the Earth, the core of the Earth, you might be interested in just going down a few kilometers, and that's where the oil and natural gas deposits are. So there's a major career path to explore for minerals, and we need that energy. Certainly, wherever there are earthquakes, we need people that understand earthquakes and can design buildings to withstand the earthquakes. We also need people who, if you're not interested in that kind of the sciences, interested more in the social sciences, we need people that can help people react to earthquakes. So after any disaster, people are going to need some assistance coping with the effects of the earthquake.
Very good. And we've gotten a final email question again coming from our friends in Alabama asking about the deadliest, largest earthquake in Mexico.
The most recent one would have been in 1986, and that earthquake caused damage, killed people in Mexico City, which is about 300 kilometers away. And it was an interesting circumstance because Mexico City is built in an old lake bed, and there was the ground motion was amplified and made the effects of the earthquake worse. But yeah, Mexico has had disastrous earthquakes.
And if students want to know more, obviously they can find out more at all sorts of websites. The USGS gives information, but your website's fantastic. Talk a little bit about what they can find.
Yeah, what we have here on our website is we have recordings of the ground motion as it is now, or the ground motion yesterday, last few weeks. We've got seismograms out there. We've collected a lot of photographs of earthquake damage over the years. We've got photographs from the 1886 Charleston, South Carolina earthquake. There was a man that made picture postcards and sold them, and we have copies of those. And we have more recent earthquakes. We also have links to the U.S. Geological Survey sites and, of course, sites that are focusing more on the earthquakes here in the central United States.
Bob, thanks so much for
My
joining
pleasure.
us. It's just been great to spend this hour with you. Thanks. And to our interactive schools who joined us, thanks so much for being a part of our program. Alaska, Wisconsin, if you've got more questions, don't forget to email them to us at live@hectv.org. That includes everybody who's watched us over the internet or television today. This program will be archived on our hectv.org website and also the iTunes U page for HCTV in about a week to 10 days. So send your friends there to look at that information and that data. We're very pleased that we haven't had a major earthquake happen while we've done the show, but we're even more happy that we joined you. Bye, everybody.